to not be included, kindly turn your camera off. So my name is Zach Shurek-Conti, and I'm a research associate at the Alan Turing Institute here in London. And I would also like to introduce my colleague and co-organizer, David Masugur, who is a PhD enrichment student also at the Alan Turing. And for those of you who are not familiar, the Alan Turing Institute is UK's National Institute for Data Science and AI. Also, for the benefit of those joining us for the very first time, I'd like to briefly introduce the topic for the seminar series, that is physics-enhanced machine learning, focusing on engineering applications. So physics-enhanced machine learning is, as most of you know, an upcoming subfield in machine learning and deep learning that aims to incorporate known physics understanding into the machine learning framework. On a side note, I'd also like to say that if any of you are interested to share your work within this remit, please feel free to reach out to either David or myself, or Andrea, who's today unfortunately not joining us, to find a slot for your seminar. That would be really great to share your work with the community. And we have quite a nice growing community now. And as for the format of this seminar, so our speaker for today, Matteo, will speak for some time, for around 45 minutes, and then we will have questions and answers towards the end. Which you may do so either in the chat or asking in person. All right, so without further ado, I'll ask my colleague David to introduce our speaker for today. And with that, as always, I thank you all.
Yeah, thanks, Zach, and hello, everyone. I would like to welcome here Matteo and also introduce him briefly. So Matteo received his bachelor's and Master of Science degree in automatic control and engineering, the University of Napoli in Italy, in 2008 and 2011, respectively. Then he received his PhD from the Technical University of Munich in 2017. Currently, he is an assistant professor at the Department of Industrial Engineering at the University of Trento in Italy. And previously, he was an assistant professor at the University of Innsbruck and a postdoctoral researcher at the German Aerospace Center, the DLR. So, Matteo, thank you very much for joining us today. We are very excited to see what we're going to learn today. And yes, we are ready.
Okay. Thank you very much, David and Zach, for actually giving me the opportunity to present part of my research during this seminar. I hope you can hear me and see. Do you see my mouse pointer?
Yes, yes.
Okay, because I use it a lot, so I'm kind of lost without it. Okay, the title of my talk is basically Geometry-Aware Imitation Learning in Robotics. I'll try to give a little bit like teaching style presentation at the beginning in order to let also the people that are not super familiar with the Riemannian manifold and differential geometry concept to be on board. And then in the second part of the talk, I will move more towards research-oriented things and works that actually we are doing together with other co-authors, basically. Okay, but first of all, I would like to say a few words, if needed, why actually we need learning in robotics. And I usually put this in my talks because actually, as David said, I studied control engineering, so I'm an engineer. And in the control community, I mean, a large part of the control community is still a bit, how to say, reluctant to go towards learning and data-driven solutions for, you know, the lack of mathematical proofs, guarantees, and so on, even if, I mean, these things are now coming. But let's have a look at basically what we have now and what we have reached. And more or less, we are somewhere here now. And we can say that basically here is a mixture of control techniques plus some nice programming skills, you know, people that have basically developed GUI. And you can just actually compose, you know, some simple motion in a sequence or in parallel and so on, put conditions, and that's it. This is, of course, there and working. It's robust, reliable, and so on. But the limitation is that it's pretty limited autonomy and requires still moderate or to high level of expert domain knowledge. And the goal of robotics, the long term, the holy grail, is basically to go in this area where you have fully to almost fully autonomous robots, or really weekly or weekly supervised robots, and not much domain expert knowledge to actually operate them. And this is basically the domain where learning starts to be fundamental in order to, again, increase the autonomy without increasing the domain expert knowledge. And in this area, I actually place myself in the imitation learning community, also called programming by demonstration in our field. So then why geometry aware imitation learning? Well, the answer is pretty easy. So we are dealing with robots, and there are many type of data in robotics that basically do not belong to the Euclidean space, okay? So the position is the typical quantity that you can treat as a Euclidean type of data, because it is, but already if you move to the orientation, then it's not anymore. No, orientation lives on its own space. Similarly, you have other type of quantities like inertia, impedance, and manipulability that belong to symmetric and positive definite matrices. What was in the past, at least in the imitation learning community, the way of doing and dealing with learning and actually retrieving from this data was, okay, let's just vectorize this data, and then we do some post processing in order to basically restore the geometric constraint or the manifold structure that a very raw vectorization of this quantity will, of course, completely destroy. And to better understand this, actually, we have this small video and an example here. So let's assume that our points live on a circle, okay, this blue circle here, and then we have these dots here, the gray ones, right? And we want to compute something simple, the mean, indicated with mu, and which is, you know, the basic of many probabilistic-based approaches in machine learning. Then what happens is, if we calculate the mean, treating these points as basically belonging to R2, to the Euclidean space, is that more or less we end up here. And then we can simply realize that this point is too close to the center of the circle to be a real one. Then what we can do, we can rescale this point, you know, pushing it back on the circle where originally it was. And then we end up here. But if we calculate the mean using basically a proper concept of distance that preserves the fact that these points are on this circle, we may end up here. So every time we do, basically, we treat Riemannian data as Euclidean, and then try to do something, some post-processing to push back on the manifold, we introduce some inaccuracies. And of course, if this is used to generate robot trajectory, and maybe we integrate, we propagate this error through our algorithm, and, you know, we end up with something that may easily go, you know, out of distribution very quickly. So I show the video again here, and basically you see that the problem is this one. So 2 points in the Euclidean space, or 2 trajectories are here, and if they have to stay on the manifold, basically we have to deform the space in order to let them working on the manifold. So this means that if we want to properly deal with Riemannian data, we should redefine, first of all, the concept of distance and use proper Riemannian distance and all the derived quantities. So the solution is then use the proper tools that, you know, have been developed by mathematicians in the framework of Riemannian geometry, also called sometimes differential geometry. So a Riemannian manifold is a very general concept. It's a small topological space equipped with a metric, so with the distance function. The type of distance function defines the property of the manifold, and it's not uniquely defined, but there are some distances that, you know, give nicer properties and are predominant in the manifold. Here on the left, you see a sphere basically embedded in the 3-dimensional space. This is the manifold where orientation lives, and, for example, unit quaternions. And here on the right, you see the cone that actually contains symmetric and positive definite matrices. Okay, so let's start giving some elements of Riemannian geometry now in order to then understand how we can deal with this data. So as I said, manifold, it's actually locally isomorphic to the Euclidean space. We can a little bit, improperly say, with an abuse of basically notation, say that it's locally Euclidean, even if this doesn't mean much from a rigorous mathematical point of view, but I think you get the sense. Actually, on each point on the manifold, you can actually define the so-called tangent space, that here it's pretty easy to depict, where basically you can define a coordinate frame and treat actually your quantities as if they were Euclidean. In order to do so, of course, we need some operation that actually let us to move from the manifold to the tangent space and back. These operations are usually called the exponential map and the logarithmic map. So the exponential map is the one that pushes a point from tangent space onto the manifold, and the opposite is the logarithmic map that actually lifts a point from the manifold to the tangent space. And another important concept is the one of parallel transport. Why we need the parallel transport? Because actually all what we will build in a moment is actually based on placing a tangent space, at some points, and then lift the data, the nearby data on the tangent space, and then use Euclidean tools to learn in this the proximity of the tangent space, and then push back the data on the manifold, and then move on to the tangent space. And then when we have to basically compare two vectors that are projected into two different tangent space, we cannot just sum them up or subtract, but we actually need to move one vector, a vector from one tangent space to the other one. So in the end, we need that all the vectors are represented in the same tangent space in order to perform operations. And otherwise, actually, basically this happens. Let me show once again. So if we just move and with typical Euclidean tools, from one tangent space to another one, we have that you see a vector that stays here is kind of completely changed, while the parallel transpose is basically a way to transfer, the proper way to transfer the vector by keeping, let's say, the orientation that it has. So you move along a geodesic connecting the 2 points where the two tangent spaces are placed, while actually preserving the directionality. So we need this kind of operations, but this actually can be defined in any Riemannian manifold. This is just to summarize basic arithmetic on manifolds. So the logarithmic map can be related to the concept of difference in Euclidean space. The exponential map is actually an addition, and the distance, this concept of distance, of course, you have to redefine the distance to be on the manifold. And the interpolation, it's also important, can be achieved through the exponential mapping, multiplying basically by the time t this difference of points in the tangent space. Okay, so now we have basically introduced our machinery, okay, the Riemannian manifold machinery. Let's now have a look at how we can use that framework into basically typical robotic problems. And a first example is the super famous, at least in the imitation learning community, framework called dynamic movement primitives, introduced in the early 2000 by Spert, Stefan Schall, and others, so working at that time at the University of California, Los Angeles. So what was their idea? Basically, they wanted to reproduce some demonstrations and generate something that was actually feasible for the robot, so to execute, so sufficiently smooth. That's why they went to second-order dynamics, and preserve the stability, okay? Because very often in robotics, you want to reach a certain position, a certain configuration, and keep it. So they had this idea, let's say, okay, let's start with the simplest dynamics that we can consider, a second order, a spring damper, actually, mass system with unitary mass. This is very famous, actually, physical model. Everyone has probably have to deal with this in basic course on physics. This is second order dynamics, linear, stable, asymptotically stable, means that from each point, so I can basically, you can imagine that I can pull this side of this spring damper system. And sooner or later, it will converge. Depending on the value of the springer and the damping, I can have oscillations, or I can have an exponentially decaying trajectory, because we usually say in control theory, no, it's a critically damped system, that converge towards an equilibrium. This is pretty nice, but of course it's quite limited. So the idea of these guys here actually was, okay, let's add to this simple system a force, actually nonlinear forcing term learned from demonstration, in order to basically execute some arbitrary trajectories, and then finally retrieve asymptotic convergence by actually killing, okay? So this force is basically multiplied by a vanishing term, so that with time vanishes, and let the system retrieves asymptotic stability towards the desired goal. This is basically the formulation, so monodimensional, but I mean, it's not so hard to extend this to higher dimensions. So these two equations, the y dot and z dot, are basically the dynamics of this guy. So the velocity is the time derivative of the position. The acceleration is basically a gain multiplied by the position error minus the velocity plus this nonlinear forcing term. Nonlinear forcing term is a radial basis function network. So we're actually these psi basis functions are Gaussian components. Nothing complicated. And I mean, this can be learned from demonstration with a pretty easy formulation. So this is the standard one. And now, of course, we want to extend this approach to basically consider data that are embedded in a Riemannian manifold. Here, for example, I'm showing ellipsoids, which means symmetric and positive definite matrices. So I can keep most of the structure. What I did, so something minor, I extended this to be multidimensional. And of course, each of these y and z are now vectors. So we need to basically deal with that. And here the weights become matrix, such that a vector. So each I is a vector, so that altogether can be seen as a matrix, such that also the forcing term is a vector. And what I have changed here is not basically dramatic. So I have the error here, so subtraction. I replaced it with logarithmic map. And the same here. This is just a scaling to prevent I acceleration at the beginning. A crucial point here is that I'm actually placing my tangent space at y, so at the current point. And this means that I'm not working in a fixed tangent space, but I have like a tangent space that is sliding over the manifold. And actually, I need just to do one integration step. This is very important because if you place the tangent space somewhere and you have points that are actually far from the center of the tangent space, you again start to introduce some deformations in your manifold and some numerical errors. While working like this, you actually minimize the error that you introduce. Is just one integration step, and then you start again placing your tangent space in the next point that comes out of the integration. So integrating this one is done through the exponential mapping. And actually, this is basically one way to extend the framework to Riemannian manifolds. The problem is now that how we compute actually the training data. So to train that guy, we need actually derivatives. So y dot and y double dot. And if you are in Cartesian space, pretty easy. We just take the difference between consecutive sample and divide by the sampling time, and do again for the second derivative. On manifolds, it's a little bit more different. So what we do is we go basically on the data. We do this is called piecewise geodesic interpolation, actually. So we place, let's assume that, for example, the two consecutive points are this one and this one, a bit exaggerated. So we have pretty closer points. So actually what we do, we then place the tangent space here on the left, take this point, project on this tangent space, assuming that they are close, so I do not deform much the trajectory. Then this gives me the difference, basically, or what is the equivalent of difference on a Riemannian manifold. And then I divided this one by the sampling time. And this gives me actually my derivative in any point. There is, of course, a bit of technicality here. So if I have to, once I have projected my data in the tangent space, usually I basically do not have to consider the geometric constraints anymore. Just to give you an example, the tangent space of the S3 sphere, the cotaneo sphere, is just a three-dimensional Euclidean space, while the tangent space of symmetric and positive definite matrices is just the space of symmetric matrices. So a symmetric matrix is just equal to its transpose, and I can simply vectorize it by taking the independent components. Then you can calculate the velocity, and once you have these velocities, you can just apply Euclidean tools basically to calculate the second derivative. And with this, learn your DMP. One of the interesting features of DMP is the possibility to change the goal on the fly. Now imagine that you have a camera, it's tracking an object, you want to catch it, and you have learned some stereotypical motion, some template trajectory reaching a certain goal G, but this goal is changing on the fly. So what you can do with DMP, you can just define a linear system that actually, with the time depending on this gain, changes the goal from G to the new one smoothly. The equivalent of this on manifold is, again, a dynamical system that instead of this difference considers the logarithmic map, this case placed at G of G nu, and then calculate G dot. You can also change, actually, the trick here is that basically you can usually interchange these two for many manifolds, smooth manifolds. And basically, if you change this one, then you have to do the parallel transpose minus the parallel transpose thing, okay, in order to interchange these two. So this is where actually the parallel transpose comes into the game. This is just a simulation. So you see that the DMP was basically trained to reach a certain goal here, and then we start switching to another one. And actually our ellipsoid here that represents a symmetric and positive definite matrix actually changes. So, and instead of reaching the shaded goal here, reaches just another one smoothly. Okay, it's time now to see a little bit of results. So we have this paper under review now, where actually we describe what I have told you so far, this geometry-aware movement primitive. So here you see some Cartesian letters, and then we have transformed this pretty simply projected on manifolds. So here on the left is quaternion, here is rotational matrix, and on the right you see SPD matrices. So how you can reproduce that, and then some experiments. So now the robot here, for example, has to fill this watering can, and then it can control basically position, orientation, and stiffness. And in the other case, the robot has to pick from a box. So we have instructed the robot to actually enter this box. So we control, in this case, the position and the manipulability, that is actually an SPD matrix, in order to, as a secondary task. And when we have to enter another box, we command the position. And to prevent that the robot, deform the trajectory too much, we have this secondary task. So the robot tries to keep actually its posture, okay? So the posture that has been demonstrated during the motion, no, in order to do this basically type of motion. So you see that here, this is the demonstration. And actually, when we try a little bit to generalize, we try to keep the configuration via the manipulability as a secondary task of the robot. And then we have this. And otherwise, I don't know, the robot could, of course, do some hit the box and so on, because of non-constrained motion. Okay, so that was basically for discrete motions, so motion that basically have start and end, but many human tasks are of periodic nature. If you imagine, I don't know, sewing, for example, or it's something that requires that you pass again and again through the same point and generate a periodic trajectory. Of course, the DMP framework was already extended to consider these periodic tasks. It's formally the same. Now, instead of a clock signal, we have this phase variable that basically goes from 0 to 2 pi and then is reset, so like a sawtooth. And the forcing term is, of course, again, it's a little bit different. So we have R, that is the amplitude of our oscillation. And then here now we have actually von Mises basis functions that basically represent our periodic signal, no? Like Gaussian over a circle. And the extension to the Riemannian actually base data, it's again pretty simple, just substituting here the difference with the logarithmic map, and all the rest, it's formally the same. Of course, we have to consider now different type of data vectorized, but more or less changes are not dramatic. Here some results, partially published, partially not, that basically this is a robot operating a drilling machine. So we have actually shown one demonstration and then made it periodic. So here we control again position, orientation and stiffness to actually guarantee a smooth interaction while manipulating this. So we basically define a variable stiffness impedance controller here, and then we can basically perform multiple holes. And you see, actually it's me now showing the holes and inspecting somehow the material. We can also change a little bit the material and the thickness, and we have basically a simple estimator, right? So we just estimate the error in tracking the trajectory and try to push more in order to, if the error is actually large. So pretty simple thing, and helps us to, in this case, make holes in a material that is, it's a different type of wood and with a different depth. So again, we can see that the robot was successfully making the holes. Next video, it's, I think, a bit nicer. I will put the audio on again just to, give you the feeling. So this is my colleague, by the way, Luca Peternel from University of Delft. And yeah, you see again here we are controlling the motion in this direction and the stiffness in order to effectively do this sewing task together with the human. So push the human in one direction and pull in the other one, not be passive. And in a moment, you will see that basically this was a real task. Run until the end. While it's coming. Yeah, and yeah, bit of suspense. Yeah, so it was really cutting down this basically piece of steel together with the robot. So again, this task was controlling the position, but not only the position, also the stiffness, in order to basically ensure the contact and actually support the human while cutting, and not only passively follow it. Okay, so we are basically going towards the end, or the last part of my presentation. So what we have seen so far with basically dynamic movement primitives is a possibility of learn actually a time-driven dynamics, where the time plays fundamental role of actually killing out the nonlinearities in order to retrieve stability. This means that we have some hyperparameters to tune in order to have a motion that, at least in the discrete case, I'm talking about the discrete case, to prevent that you have some overshoot, or that you kill this nonlinear forcing term too early and then you just linearly converge to your target. And then there was actually in the last more or less 10 years, or a little bit less, a lot of effort to learn actually stable and autonomous dynamical systems. So systems that do not depend on time input in order to generate the motion. So where basically you learn actually an entire vector field, and potentially you can also generalize in areas of the state space where you don't have demonstrations, because you have a certain shape of your vector field also far from the demonstrations. the idea is nice, and I mean, I also developed a few approaches in this field that I'm not going to mention today, but then the problem that we started to face is, okay, now what if we want to have an autonomous system, so time independent, that actually it's stable and evolves on the manifold? And then the idea was actually very, very similar, but we had to actually use a particular type of learning. So we could not actually learn simply a forcing term in order to guarantee stability, but we had to rely on some diffeomorphic mapping. So the idea is basically this one. Again, exploit the tangent space. And in this picture, I'm just placing, for simplicity, the tangent space at the goal. But as I said, this can introduce some distortion. So you can, by parallel transposing it, just consider a local tangent space placed in each point of your trajectory and then have it sliding on the manifold. And this is a way more accurate than that. So we can define very simple linearly converging, where linearly has to be, of course, considered on the manifold. So linear on the manifold, it's of course some kind of geodesic curve. If you imagine a globe, so point like the path between 2 points, it's of course not a straight line, but it's a piece of geodesic. But anyway, this is the tangent space projection of it. And then what we can do is, from the demonstration, we can learn a mapping, okay, that just transforms this vector field into this one on the right through the mapping, and it's Jacobian, so the derivative with respect to the state. And this is guaranteed actually to preserve the stability. So it's time independent and stable. And in case we have to go back, of course, we can go back. So the mapping has to be smooth, okay, because we have to calculate the derivative, invertible, and with continuous inverse, because we also have to invert actually the Jacobian matrix. And these are basically the properties of a diffeomorphism or diffeomorphic mapping. Just to give you a few little hints on this, basically, so this is geodesic system, okay? Again, placing the tangent space in the current point, or via the transformation, placing it at the goal. It's for a few manifolds, it's similar if you consider parallel transport in between. And then, yeah, just the equivalent of a linear dynamics. No, this is an error here, multiplied by a scalar gives you the velocity. And it's the same. So this is actually the so-called global coordinate, and that where actually you define a velocity field, and then you start to integrate it. And this creates from an initial point to the goal a piecewise, a piece of geodesic motion. So that's the simplest thing that you can do on a manifold, and that's the simplest dynamics that you can actually describe on your manifold. And then what you can do, again, as I said, from your data projected in the tangent space, you can learn a diffeomorphic mapping that actually takes as input this general global coordinate log x, and multiply this by the Jacobian computed at the same point, the same gain, and gives you a dynamics that, for example, here follows this blue line. Now, learning this diffeomorphism has been quite studied quite a lot. Maybe you are familiar with the normalizing flows. Probably this deep neural network that actually is used to so originally proposed to actually learn random nonlinear distributions, getting as input a Gaussian. So some people have, of course, exploited normalizing flows to learn this diffeomorphism or other type of deep neural network. What we have done instead is to make one step back and use a more, let's say, traditional approach, Gaussian mixture models, showing that under which conditions a Gaussian mixture model is actually a diffeomorphism, which are, I mean, pretty soft conditions. And we have, I mean, again, in a paper that is under review, show that this is more data efficient, means that we can accurately learn this diffeomorphism from a few data. And also, I mean, time efficient, because, I mean, training normalizing flow, it's quite intense. And also you have less hyperparameter. In a Gaussian mixture model, you mostly have one hyperparameter, that is the number of Gaussian components that can be, I mean, with a little bit of experience, you honestly choose it by hand after a while that you use Gaussian mixture models, or you can simply do a grid search among reasonable values, and that's it. And yeah, this was not the same for actually deep neural networks. We also have another paper in the pipe where we use deep neural networks, but we had to do a proper hyperparameter search on the cluster in order to get good results. So this is the type of experiments that we have done. So this is actually our dataset I mentioned already before. I will show the link later on where you can actually download it. It's an existing dataset that we have basically projected on orientation and SPD manifolds. So nothing, no rocket science. And this is an example where actually we were controlling position and orientation of the robot in order to do this wine stacking. One of the criticisms was that I could have chosen a slightly longer battle, because it's really fitting that quite, precisely, but I mean, that's it. And yeah, now we change the goal. So the demonstration was done always reaching the same goal, and then we can change the goal, because this is one of the properties of dynamical system, but very simply converging towards another goal. I hope the video is not too slow now due to the lag in the connection. So this is yet another goal, and now we change also the orientation basically of the rack and still perform the same task successfully. And I mean, this is of course there is large tolerance in this, but still you have to be somehow there, otherwise you don't make the task. And this is a cooperative drilling. So here we are basically controlling the stiffness to below while approaching drilling pose, and then now we have high stiffness, so we have a variable stiffness profile, and now you see that basically, so the robot was actually compliant or with the low stiffness at the beginning, because you have to just rotate and lift this one from the container, and this piece of wood, it's relatively light, so you have to like unstack a little bit, and you saw that was, I mean, relatively smooth due to the fact that the robot has compliance, and now it's becoming stiff. So you see that, I mean, you can drill and the robot is supportive. Of course, I mean, this is not an industrial robot, maybe you are familiar with it, so there is already some elasticity into the joints. So even if you set the maximum stiffness, the robot moves a little bit, but still, yeah, you can do this type of tasks. Okay, just to basically summarize. So I presented today something, I mean, a little bit of Riemannian geometry framework and some ways of extending traditional imitation learning or programming by demonstration framework to the Riemannian manifold. We have started to release our code, actually, even if papers are not published yet. But I mean, just to serve the community, we have a MATLAB implementation. This is also a long story. I'm trying to, move from MATLAB towards Python, but still, my proficiency level now, it's kind of similar. So Python is overtaking finally. But yeah, this one has been done in Python, and it's basically the geometry aware DMP that you can download and try. We have tested actually 4 different manifolds, so symmetric and positive definite, unit quaternions, rotation matrix, and SE3, that is basically the composite manifold where you have position and orientation. We will probably release, I mean, some other code, but I mean, you can actually check or email me if you are interested, and I can even, of course, I can share some development version, even if they are not super clean, with you, so that you can try it. Okay, thanks a lot. I think I was running a little bit, but yeah, hopefully we have time for questions.
Well, thank you very much, Matteo. That was really, really cool. I love manifolds, so I definitely found that cool.
Okay.
I'll open the floor for questions. If there are any questions, please ask in the chat. I know that Peter had one before, but I'm not sure you still want to ask it. In the meantime, I do have one or two questions. Let's see. Okay, then I'll go ahead. So what I wanted to ask primarily was when you started to talk about the Riemann manifold geometry, you make an assumption right there. So you're assuming this kind of spherical manifold. Spherical. But it is a manifold, right? So what assumption? What is the influence of that assumption in the work? So because of course there are other kinds of manifolds that you can choose.
Yeah, well, actually, so if we stay in the smooth manifolds, so far we have considered not only the sphere, but also the cone that basically describes symmetric and positive definitive matrices according to the affine invariant distance, or one type of distance on the SPD space. And these are pretty different. So the sphere has this problem of basically you have the top and the bottom hemisphere, where actually you have antipodality problems. Now, if you consider this to represent robot orientation, so a point that is on the hemisphere and the conjugate one represent the same orientation. So this is a typical problem that you have to face with, and usually as a robotic, what you do, you force your data to be in one of the two hemispheres. Okay, so this is something that you have to keep in mind. In this type of manifolds, you don't have this problem. So points are like uniquely defined, so they are different managers. But you have two problems. So the manifold is unbounded, okay, because I mean I just cut the cone here, but this is just growing. And so it's non-compact manifold, and you have also this point 0, 0, 0 that creates a lot of problems. I mean, can create problems, zero divisions and stuff like this. So in this case, I mean, for the non-compactness, it is okay because you have a trajectory. So your trajectory will be compact anyway, so you will stay somewhere. And we are forcing our system to be stable. So stability means that you will not diverge. So you will not reach point at the infinity, which is good. For the 0 point, we don't have a real solution now, apart from like staying far from it. That's basically what we are doing now. But the approach is let's say rather general, apart from properly defined these mappings. So each manifold has these mappings, the logarithmic map and basically the exponential map, that you can define on each point on the manifold. But what we didn't try, it's in some complex manifolds, the functional expression of the logarithmic and the exponential map can even change. So on the sphere, you have the same functional expression, just placed, you have to change the point where you do it. Of course, this gives you different tangent spaces, but because it's a function evaluated in a different point. But for some manifolds, even the function changes, and this is something that we are still trying to investigate.
Okay. And my second question, I'd like to ask about, so if you have a different robot with different specs, right? Can you map this on this manifold, or can you reuse the information that you have from the previous robot? So in a way, because of course, there are similarities, right?
Yes.
Similar manifolds. This is something I'm working on right now, but they're a different application. So this is definitely interesting for me as well. There's obvious geometry transformations between similar state spaces.
Yeah, of course. I mean, apart from the geometry, so what can be transferred relatively easily is the manipulability, actually. So the manipulability basically describes in which direction you can move more freely and in which direction your motion is constrained. So if you imagine the robot like stretched like this, of course, in this direction, you cannot go forward much, right? But you can go up and down freely, right? So your manipulability is like, so if you describe a manipulability profile, and indeed there are papers that actually show this, like transferring from human to the robot and some other stuff. I invite you, if you're interested in this, have a look at recent work from Sylvain Calinon group where actually they do manipulability transfer. So manipulability can be transferred with little effort, I would say. Position and orientation, you need transformations, right? So you need maybe to rotate the base of your robot and stuff like this. And you can have, you have to rescale usually. Imagine you have a very big robot and a very small robot, then you have to rescale your trajectory.
Let's say in this new robot you have some data, and in the other robot you have now, of course, quite some data. Can't you use the some data to indicate how to transform your old manifold?
Yes, of course. You can, I mean, if you assume that you have the same manifold and you have the data, then you can find the relationship between them and actually, I mean, redefine the distances and so on. So this is, of course, possible using a data-driven approach.
Okay, very cool. Thank you. Are there any questions from the audience? Before Peter seemed to have a pressing question. I wonder if
someone raised
Yes, it was me. It was me. Thank you very much, Zach.
I'm sorry, I don't want to put you on the spot. I'm sorry.
No. Thank you. I had a very naive and a silly question. In the mapping, when you project your dynamical system onto a manifold, it almost seemed like it's a little bit linear, the system. Does it matter? And am I wrong?
You mean here?
Yes, and in the actual equations, they seemed to be linear in G. Is that an important factor?
Well, it is not linear. So I mean, this is like the equivalent of a linear system on the manifold.
Yes.
And of course, this generates, so linear system in Euclidean space generates straight lines. This generates piece of geodesic. So that's it. So the only thing is that you adhere to the manifold geometry, and whatever it is your manifold, it will generate a path that stays on the manifold. And then we don't want this. I mean, this is good because it's guaranteed to be stable. We can use some Lyapunov theory to prove that you will always converge to the goal and so on. But this is only part of the equation. And then we want to do, for example, the blue line here. And how we do this, we pass this through a nonlinear function here. That is...
that's why you mentioned normalizing flow. I understand. My question was the underlying physical system in the Euclidean space. Can it be highly nonlinear, the underlying dynamical equations?
Yes, it can be. And I mean, in the Euclidean case, and I mean, in general, you can learn directly a nonlinear system and enforce some Lyapunov conditions on top of it. This is possible, and then you can pass through this. I have, for Euclidean case, I have actually a paper where I show that I was doing incremental learning, okay, and then I show that if I start from a system that is just generating straight lines, and then I show a pretty complex path, then it takes, a lot of time to, slowly move to this, not a lot, but takes time to basically converge to that one. While if I was giving something that was already in that direction, like a piece of sine function and so on, I show that actually it was quicker to reach incrementally the other one. So of course, if you start already from a dynamics that gives you what you want, it's clearly beneficial for the learning. And
thank you very much, and thank you for your talk.
Yeah, just another point is that actually this is a diffeomorphism, so it has a lot of, so it has to be bijective, continuous, and so on and so forth. And it's relatively easy to break these conditions with real data. All right, so if you just have two trajectories that intersect and continue, one on top and one on the bottom, then you already can break this condition. Then you can do some averaging and so on to cope with it. But this is something that I really like to overcome. So to have, let's say, less constrained learning strategy, but still to keep stability.
Thank you.
I have also a naive question. Sorry, one more naive question from me. The manifold, the spaces you showed in the beginning, are they bound by the eigenvectors of the system, or are they the main variables? So in the beginning you showed that.
The very beginning.
Yeah. So like in these state spaces, in these particular state spaces. Oh, I see. Sorry. Okay, I've answered my question.
Okay. Good.
All right. If any other pressing questions. All right, seems not. But meanwhile, I'd like to thank you so much, Matteo. This was really cool, and I hope that we can see more geometry oriented, dynamics work on this kind of stuff in more in future talks.
Working on this topic also, Zach, or?
Sorry?
Are you working on this topic?
Yes, I'm actually working on this topic, but from an energy dynamics perspective.
Okay. I have a question for you then. Just let me use 5. So you know that, I mean, if you go to this geometric deep learning, so people, I mean, I don't know all the literature, of course, but all the paper that I read is basically they are using this. I think it was from John Nash, this embedding theorem. No, so you know that a smooth manifold can be actually embedded in a sufficiently large Euclidean space. And actually, they use this fact in order to calculate the Riemannian distance. And once you know the Riemannian distance, then you can define all the rest. But do you think we can overcome this? And I mean, what I do instead is I usually study known manifolds like SPD and so on, for which some mathematicians have derived the concept of distance, and from the concept of distance, it's pretty easy to define the logarithmic and exponential maps and the rest. And the pure data-driven approach is, okay, let's consider super higher dimensional embeddings. No, and then just do an average in this higher dimensional space and then say, okay, this is the distance. Can we find something in between?
I don't know, it's a hard question. So I myself, I don't work directly with geometric deep learning, but the assumption I make is that higher order systems actually exist on low dimension manifolds. So, which I guess is the same thing.
Yes.
And and I'm actually right now working with relatively simple examples. So it would be naive of me to kind of like give you an answer on what you asked me. The thing is that what I'm exploring actually is looking for the distance between different systems, rather than looking at distance, the distance, the non-Euclidean distance between, let's say in your case, it's the same system, but it's different scenarios of the same system, trajectories. In my case, I'm looking at different systems and seeing how we can find these geometric transformations.
Okay. The minimum distance between two different, completely different
but that are related
spaces. Oh, okay, that's
because the state spaces are very similar. So if we find we can represent this geometrically, then you can actually you can find morphs, you can find transformations between these governing spaces. And here the goal is that we are challenging the typical, black box methods. In my case, we are doing energy forecasting, so it's a little bit different to your application. And we are challenging the black boxness of these kind of typical data-driven models that don't give you much information. Also, they don't generalize very well. So the one way of tackling this is by dealing with rather the state space instead, and which is innately governing, right? So, and how do we leverage these physics-driven state spaces into this data-driven framework? So that's why I asked earlier about finding transformations between
different robots.
Exactly, yeah. And I think it's very powerful. I think we are slowly working towards a new kind of machine learning that's catering for engineering dynamics. And I'll be happy to kind of involve you in what we are doing. And
it will be, I mean, just to.
Yeah. Also, your colleague who spoke before you maybe a few weeks ago also was interested in this, so it would be very cool to have a chat. And anyone who's listening, perhaps.
Okay. Well, thanks a lot.
Thank you so much, Matteo. This was really, really interesting. All right, so I won't take more of your time. And say thanks to everyone. David, thanks once again for your assistance. And we will see you again in 2 weeks. We'll see you in 2 weeks' time with a new talk.
Yeah, thanks, everyone.
Bye, guys. Thanks, Harry.